Okay, so welcome. This is going to be a continuation of the lesson that was on last Thursday. And if you take the notes on this and you turn them in, then in Cornell Note style, and you followed the Cornell Note rubric that's under doc sharing, you'll get some extra points. Your notes will be graded per that rubric, so please make sure if you want to get the maximum number of points that you look at that and make sure you follow and include all the pieces that it's asked you to include. So we'll do a quick review of what we talked about in class the other day, and then we'll move forward with the rest of what we didn't get the chance to talk about in class. So here we go. The essential question we had from in class is, why do you use number lines to assist you in estimating the value of the square root of a number? And so if you need to pause for a second, go ahead and pause and then start when you're ready. Remember when we did this, what we looked at is we said that this is the same as saying 3 times the square root of 200. And then we broke the 200 down to factors of 200, where one of the factors is a perfect square. So we said this is 3 times the square root of 100 times the square root of 2. And so therefore we got 3 times the square root of 100 is 3 times 10 times the square root of 2, and the solution was 30 square root of 2. So that's kind of a quick review on that piece of it. Then we created a number line, and we put these different numbers on the number line, and we found out that 35 was really close. Square root of 35 is really close to the perfect square number of square root of 36. So when we put that square root of 35 on the number line, we found 6, which was the same as the square root of 36. And we put the square root of 35 right next to it. I'm going to put it above so you can see it, because square root of 35 would be right next to the square root of 36. We also found out that if I put 5 on here, it's the same as the square root of 25. So the square root of 21 is going to be, and we also know that square root of 4 is, excuse me, 4 is the square root of 16. It's also 4. So our square root of 17 is going to go right next to here, because it comes right after the square root of 16. And the square root of 21 is also going to be between the 4 and the 5, because, and it's going to be closer to the 25, because if we think about counting, the square root of 16, square root of 17, square root of 18, and so on, and 21 is going to be closer to 25. Now, once we placed all of these things on here, and then of course square root of 3 would be somewhere between 1 and 2, because 2 is the same as the square root of 4. And 1 here would be the same as the square root of 1. So the square root of 3 is going to go up here closer to the 4. We have the square root of 1, square root of 2, square root of 3, and square root of 4, and so on. Okay? So in order to, now that I've got those on there, I can figure out approximately what the decimal value is of these irrational square root numbers. So when I look at this, let's just take a quick look, and we'll look at, if we have the number line, we start from at 1 and we go to 2. We know that this is the square root of 1. Then we've got the square root of 2. And we've got the square root of 3. And we've got the square root of 4. So if I want to find the decimal value for the square root of 3, I know it's between 1 and 2, so it has to be 1 because it comes after 1. And there's a decimal number that goes with it. To figure out that decimal number, we can look at how far from 1 to 3. And I can see that there is 1, the distance of 2 from 1 to 3. So I can write that, and that 2 is out of a total of, to get to the next perfect square number, it's out of a total of 1, 2, 3. So I have 2 lengths out of 3 lengths. Okay, so the square root of 3 is pretty close to 1 2/3. And if I round that off to the nearest tenth, it comes out to be 1.7. And if I put that into the calculator, it's going to actually come out to be 1.7 something. So that's the basic idea of how to figure out a decimal value there. There's a second way to estimate square roots, and this one's a little bit, probably a little more challenging, but it's a good thought, and it will help us get to even probably more precise decimal values than this. And this method goes way back to Babylonia, and they figured out how to do the square roots clear back then with the mathematics. So basically, the first thing you have to do, still again, we have to determine which two consecutive integers the square root of 21 lies between on a number line. So if I have a number line, the square root of 21 is going to be between 4, which is the square root of 16, and 5, which is the square root of 25. So the 21 lies in there somewhere, and it's closer to the 25 than it is to the square root of 25 than it is to the square root of 16. Okay. So once we've done that, we're going to just kind of guesstimate an approximate decimal place between the two integers. Okay, and we're going to use our tenths place. And so we know that the square root of 21 is a little bit more than half. So we're going to use something that's a little bit more, a decimal number that's a little bit more than half. It's going to be 4 point something because it's between 4 and 5. So we can figure that out. We can figure kind of the approximate decimal value out. We can use the method we used before to kind of get us close. And then we can use kind of just a guess and check type method. So I know that kind of to get us a little bit close, I know that 21 is, there's a distance of 9 from 16 to 25, and 21 is 4 away from 25, so it's going to be 5 away from 16. So there'd be a 5/9. So that's going to give me a little more than half. So let's make it like 4.6. So we're going to call that number that we just chose, 4.6, R1. So we're going to call that 4.6. And then we're going to use that R1 to figure out a number that's even closer to what we guesstimated. And we're going to call that R2. And we're going to keep doing that until we get to the point of we've got a number that we're satisfied with. And we're only going to use, we're not going to use too many decimal places, but you could do this to several decimal places to make this work. So what you're going to do, and this is going to replace the R1s with the 4.6. And kind of repeat that process, go through the process and figure out what's happening. And you have X, which is the original number of the square root of the square root of 21 piece, or the 21 piece. And the question that we have though here is, why does this work? Because basically what we're doing is we're finding an average between, kind of continuing to find the average or middle number between two numbers, and we're getting numbers that are closer and closer and closer together. So every time we take those two numbers and divide by 2, with our new numbers that are closer and closer together, we're getting closer and closer to the number that we want. So it estimates square root of 6 to the nearest tenth. So looking at the number line, square root of 6 is between square root of 4, which is 2, and the next one, which would be square root of 9, which is 3. Okay? So we have square root of 4, square root of 5, square root of 6, square root of 7, square root of 8. So 1, 2, 3, 4, 5. So there's a distance of 5 there. And so square root of 6 is not quite halfway, because halfway would be right about here. So we could say that that's about, let's say it's about 6 points, or it's about 2.4. Okay? So going back, we've got our equation. We know that our R1 is going to be about 2.4, and we're going to put it into this new equation, the R squared, R sub 2. And let's do that. So R sub 2 equals, and we want our 2.4, which is what we're saying that's probably about 2.4, so let's put 2.4. And then plus, we're going to do 6 divided by 2.4, because that, if we're looking for the length of the side of the square, let's see, the square is an area of 6. What we're saying is this side is 2.4, and that this side is, we can figure out how big this other side is. We don't know. We want it to get closer and closer, so that this number here and this number here end up being the same number. And so that would be the same number. We know it's a square, so we're taking the 6 divided by the 2.4, because we guesstimated that's probably about the right size to get those two numbers to be the same. It probably is not going to be. That this, again, then that's how we're finding the average. We're taking a number and we're taking the other number, and we're going to find the average, because we're going to divide that now by 2. And as we get those numbers closer and closer together, then we're going to make it work. So let's make sure we've got our full equation, and so we do. And as we calculate that out, we get a number, and that number, using our calculator, is the number ends up being about 2.45, so we ended up pretty close. And if I round that off, if we're talking tenths, then this would be approximately 2.5. So now we're going to do this again. Okay, we're going to do it. So now this 2.5 is our R2. So now we're going to do an R3. So we're going to use a 2.5 plus 6 divided by 2.5, and that whole thing divided by 2. So again, I'm going to use my calculator and figure that out. 5 plus 6 divided by 2.5, and then divide that by 2, and we get 2.45. So we've got the same answer here, and that's again approximately 2.5. So we keep doing this process like what I showed you here for each of these, here and here, until we get the same answer both times, or more, 2 times in a row. And then we know we've got a pretty close, accurate response. And so, and even the 2.5 was rounded to the 10th, but the 2.45 is going to be even closer. And we can, if we use the 2.45 in here, then we would go another round and we get a 3 decimal answer, and so on, and we can keep going until we get a pretty exact answer for this. But we're close enough at the 2.45, or if we want to just use 1 decimal place, depending on what you're asked for, at 2.5. So that's the basic idea of how to do that example, that situation. So the next thing that we talked about in the lesson is simplifying radicals with variables. And so keeping in mind what square root and squaring means, we know that if I say 2 squared, I get 4. And if I say square root of 4, I get 2. And it's positive 2 because when there's no symbol out in front of the square root sign, it always means positive root of that. And then, so I could also write that as the square root of 2 squared, and that would give, because 4 is also 2 squared, and that would just give me 2. So what I can see is squaring is the opposite of square rooting, and square rooting undoes squaring, just like multiply undoes divide, and divide undoes multiplying. They go together. And so that's what I've got here. So when I'm looking at this, when I say the square root of x squared, my answer is just going to be x, because the square root undoes the squaring. So anytime I see a square root sign, I want to look for things that are squared. Okay? And just like with when we did earlier, let's go back here. There we go. We did this problem. We broke that down into 2 numbers, and we chose one number that was a perfect square. 100 is 10 squared. And so I can, if I have numbers that don't come out as exactly perfect squares but could be factored into perfect squares, I'm going to break it out that way, just like I did here. So as I'm looking at this, I know that I can rewrite x cubed to be the square root of x squared times x. And that gives me x cubed. So now I can break that apart into 2 separate things, where I take the square root of x squared and square root of x, and I'm going to get square root of x squared just gives me x, so I'm going to have x times the square root of x, because I don't have any numbers to take the square root of x. And that gives me an exact answer when I leave it in that radical form with the square root sign on it. And if I change it to a decimal, I do not get an exact answer, and that's an important piece to remember on things. Sometimes you want exact answers, and sometimes you want to get the decimal. So pay attention to which one you need or which one you don't need in terms of what you're being asked for. Now, x to the 4th is the same as x squared times x squared. You could also write it as x squared either way. And so your answer comes out for this one, for this piece, that's x times an x, which is just x squared. If I look at it the other way, x squared squared, if I take the square root here, right here is going to undo this square root here, so I end up with an answer of x squared. So either way you write it, it works. If I end up with x to the 5th, that's the same as the square root of x to the 4th times the square root of x. And we know from above that x to the 4th is x, the square root of x to the 4th is x squared, because we can write it this way. So let's write that out just a little bit so you can see it. X squared times x squared times x to the 1st. So you've got an x, and the square root of x, which gives me x squared square root of x. Okay, so we did that with variables, and you're going to continue using this idea with variables, but we're going to get a little bit more complicated here. So we're also going to use it with our numbers as well. So as we're looking at this, I can break this apart. I can say the square root of 25, and I can work with that, times the square root of x to the 10th. And I can break each of those apart and work with those. I know that the square root of 25 is 5. And I know the square root of x to the 10th is, x to the 10th is like saying x to the 5th squared. X to the 5th times x to the 5th is going to give me x to the 10th. Or you could do a bunch, write it out again, x squared, x squared, x squared, x squared, and so on. Figure that out. So I end up with 5x to the 5th power. Okay? This one, again, it's going to be a little bit more challenging than the first one, but we can still do it. We're going to separate the number part from the variable part, times the square root of x to the 7th. And I'm going to break the 20 up into the square root of 4 times the square root of 5. So I can simplify the square root of 20. And then I'm also going to do square root of x squared, square root of x squared, because that gives me now 4. Square root of x squared gives me 6. And then it's just the square root of x to make 7. So square root of 4 is 2. Square root of 5. So we can't take the square root of 5. We have it come out evenly. We want an exact answer here. So we have this first x squared, square root of x squared, it undoes it. So we've got 1x, 2x, 3x's times x to the square root of x. So if I'm writing that, I now have times x cubed times the square root of x. Now I'm going to simplify that back together and end up with 2x cubed and square root of 5x. Okay? And if I do this next one, it's variables. So I'm going to separate the two variables. So I've got x to the 5th and y to the 12th. So that's giving me square root of x squared times square root of x squared times the square root of x. That makes 5 x's like it shows. Times, and then I'm going to write the y just a little bit differently, so it's a little bit faster. So I've got y to the 6th squared, because if I have two sets of y to the 6th, I have y to the 12th, and I end up with, and again, if you need to write it out like I did for the x squared to help you see it, go ahead and do that. So you'd have y to the squared, y squared, y squared, y squared, and so on. But you'd have to write about 6 of them out to do that. So for this part right here, I've got the square root of x squared, so that's 1x, x to the 2nd, and then square root of x. So let me write that down. So I've got x, square root of x, times, and then got y to the 6th. So if I rewrite that, I'm going to simplify that and put all the stuff that's not under the square root sign out front. X, y to the 6th times the square root of x would be my solution. So there is the simplified version of that. One of the other things you need to understand is something called rationalizing the denominator. Now, the reason we do that is because although we do things and use things at times when the square root's in the denominator, and sometimes we actually want to get it there, most of the time it's like writing the fraction in its simplest form, or finding the equivalent fraction in its simplest form. We don't leave the square root. Typically, don't leave the square root in the denominator. Now, when we're working with the mathematics and stuff, sometimes we do because it's going to help us get to the solution a little bit more easily and so on. But typically for an answer, we don't leave the square root in the denominator. So how do we get rid of that? Well, we know that if I multiply the square root of 3 times the square root of 3, that gives me the square root of 3. And the multiply number by itself, I get that square. And the square, remember, undoes the square root. So since I have a square root of 3 here, I want to get rid of that square root. So to get rid of the square root, I'm going to multiply it by another square root of 3, because that gives me what I just wrote here, which just gives me 3 as the denominator. Now, if I multiply this by the square root of 3, I have to multiply the numerator times the square root of 3, because I've got to multiply. I don't want to change the value of what I have here, so I'm multiplying by the fraction that is equivalent to 1. So remember, any fraction where the numerator and denominator are exactly the same gives us the number 1. So I'm multiplying 2 over the square root of 3 times the number 1 in the form of square root of 3 over square root of 3. And I chose that because it helps me get rid of my square root sign in my denominator. So as you can see, as we go down the page, I've got 2 times the square root of 3 over the square root of 3 squared, which is what I wrote over here. And then I simplify that, and I get 2 square root of 3 over 3. So as I look at this one, I see that I've got a square root sign in the denominator, so I need to rationalize the denominator. So I want to simplify it down and get to something that doesn't have that in the denominator. So in order to get rid of the square root of something with a square root, I need to multiply it by itself, because squaring then does square rooting. And so by square it, that means I have a number times itself. And so if I have square root of 6 times square root of 6, I've then done the square root. And so it's able to go away. So that's exactly what I did right here. I multiplied the denominator by the square root of 6. So I'm going to multiply the whole fraction there as by the number 1. Therefore, I have to put square root of 6 on top and on the bottom of the fraction. So once I've done that, I end up with this as I go to simplify it, so it's now all together in one fraction. I end up with, because I multiplied square root of 6 times square root of 6, I end up with 6x, and I get that as my fraction, but I'm not quite done yet, because 24 over 6 can be simplified even more. So I end up with 4 times the square root of 6x over x. Okay, so basically you're just working on simplifying fractions like you have all the time before in your way back in elementary school when you're working with just fractions with just numbers. It's just now you're learning how to deal with the square root sign in order to simplify and do that process of simplifying. One of the last couple things we need to talk about is evaluating a variable square root expression. So you'll see something that says evaluate the square root of x plus 10 when x equals 6, something along those lines. All you're doing is this. We didn't know what that was, but now we do, because I told you that x is 6. So all you're going to do is you're going to replace the x with the number 6. So I'm going to write square root. I'm going to put 6 here in place of the x, because that's what I told you it was, and add the 10. Once I've done that, I end up with simplifying that, square root of 16, so the solution is a positive 4. Okay, it's positive 4 because when there's no number or symbol sign in front of the square root sign, it indicates a positive root for that. It indicates the answer is the positive. Because I know negative 4 times negative 4 can make 16 too, but if they wanted the negative solution, they would tell you that by putting a negative in front. Okay, so anytime there's no sign there, it means it's a positive. We want the positive root. So here's our next one. It says evaluate square root of 8x plus 2 times square root of 12x when x equals 4. So again, you've got an expression, it has variables. I'm telling you what that variable is worth. And they want you to find the exact radical form and the approximate value of the expression to the nearest hundredth. And that goes along with what I was talking about earlier. If you leave things in square root form, like square root of 12, that's giving you the exact answer. But if you change it to a decimal, it's giving you an approximate answer. So we'll look at that when we get down to the bottom. So the first thing I have to do is replace the x's with the number 4. So that's what I did here. And then once I've replaced it with the number 4, I actually work out what's there. So I'm going to say 8 times 4 and 12 times 4. So I get square root of 32 plus 2 times square root of 48. And then I'm going to simplify each of those. So the 8 times 4, the reason I went ahead and multiplied it back together is because I needed to be able to figure out, because 8 times 4, that 4 is a perfect square number, but there's a better one. We want to always go with the largest perfect square number, like the 16. We also can see, yes, this 4 works here is a square root number, but I think there may be a bigger one, so we need to look at that, and there is one that's 16. So we always want to go with the largest factor that's a perfect square number. And so once I've done that, I can take the square, break it apart, take the square root of each part. And so I end up with 6 squared root of 16 is 4 times the square root of 2, and then I've got the 2 out front. Remember, that means 2 times that, what's under the square root sign. This means 2 times the square root of 16. So I've got 2 times, and the square root of 16 is 4, so 2 times 4 is 8. So I end up with 4 times the square root of 2 plus 8 times the square root of 3, and that's my exact answer. So when they say find the exact radical form, like they did right here, that is exactly what you got right here. But then it said find the approximate value. So that means I have to change them all to decimals. And so when I take the square root of 2, I multiply that answer times 4. And when I take the square root of 3, I multiply the answer times 8. And I end up with approximately 19.51 to the nearest hundredth. Okay. So here's another example of that exact same thing. It's a little more complicated expressions that we're working with. And so you can see that the first thing I did was I substituted in for the x. Then I simplified each of the parts in between the addition and subtraction signs. And then I continued to do that until I got down to the bottom, and then I can figure out I get the exact answer. Right here I get the exact answer, and here then from there I can go and figure out the approximate value. So I know that in order to do that, you have to understand that the first thing means 2 times the square root of 3. So 2 times the square root of 3, square root of 3 is approximately, 2 times square root of 3 is approximately 1.7. And then subtract 15, and that's times the square root of 2, and that's approximately 1.4. So once I have those figured out and calculated, then I can get my specific answer. In this case, I rounded to the 10th, so you're going to have an answer to the nearest 10th. And with that, we did have a lot of stuff that we kind of had to go over and talk about for this week and for starting from Thursday last week. And so I'm trying to get you through that. After this week, we should slow down and not get quite as many new things at one time. I tried to make it so that we weren't getting too many brand new things all at once. But there was a lot of stuff to kind of go over and talk about and think about this time around. So hopefully this helped you as you go through your lessons. And good luck on that, and have a great rest of the day.